Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 123, Digital 3. Today we are going to discuss RAM, which if we remember right is Random Access Memory, which we are capable of reading and writing. And obviously, when we read it, it's non-destructive. We want to keep a copy. Basically, a reading is all it is making a copy of it and writing to it, and that is going to erase what was previously there. Another characteristic of RAM, which again, random access memory, it's volatile in the fact that it's only temporarily there and it requires power. And as soon as power is gone, it evaporates. And it's, like I said, because it's volatile, it's oftentimes used just for short-term operations. So there are two major categories of RAM. The first one being SRAM, static RAM. And then the other one being DRAM for dynamic. And the major characteristics that distinguish between these two guys, SRAM uses latches, whereas DRAM uses capacitors to store information. Okay, so SRAM, it's a little faster, but more expensive. DRAM, a little slower, but cheaper, and it's a smaller size. Okay, and we'll discuss why these things are. The SRAM is faster and more expensive, and DRAM is slower and cheaper and smaller. Additionally, DRAM, because it's a capacitor, if we remember right, it's two parallel plates stuck together. It needs to be refreshed constantly, whereas SRAM, a latch is going to store a 0 or 1 indefinitely as long as we said there's power. Okay, so let's take each one of these individually, and since 1, 2, let's start with 1. So SRAM, static RAM. Okay, as we said, it's made up of latches, and those are individually inside a memory cell. Doesn't really matter what's inside the cell, but each individual cell has 3 connections: data in, data out, and a select. Okay, so the select and how they're organized here is, again, they're still in our arrays. Here's a 3-bit row. And here's another 3-bit row below it. And we want to write to a 3-bit row. All the selects for a particular row are tied together. So that's row, let's say 4, that's row 5. Okay, we want to go ahead and write something to row 4. So the first thing we got to do is we got to select it. So row 4 goes high, all the other rows remain 0. So now which row is activated? That one. Okay, now it's capable, and let's say we are doing a write operation. What we do is place a 1 or 0, and let's say we want to store the number 7, 111, into this guy. We place our data on our D-ins, and it's latched into those guys. And if you remember right, how we're doing that is our input buffers right there, and our output buffers. I'll draw this again too, a little bit neater. Where, oops. Yeah, I'm going to draw this the whole thing again here. Just for now, just think the data in is coming in through there, and I'm going to draw how that works. Okay, so a read. So first off, let's finish up write. So write was placing 1 or 0 on DN. And we'll go back to the buffers. I don't want to confuse this drawing just yet. I'll confuse you later. Okay, so read it, opposite of writing. Yep, got to select it again. To read what's on data out. In this particular case, 1, 1, 1. Okay, so in the case of an 8x8 two-dimensional array, where bytes are organized in rows. So it's 8 rows, 8 columns. And like I said, bytes are organized in rows. All the selects, just as we've done up here, are all tied together. So all the D-ins and D-outs connect to an 8-bit or a single byte data bus and register. So you may see a problem here. Well, hey, why is the data in and data out connected to the same data bus, which is connected to a data register? Well, what's the problem there? What am I reading? Data in, data out. Well, that's how your input, register input and output control, which is what I was trying to draw earlier. Register input, output control works. Basically, when it's in a write mode, you want to enable the input buffers and disable the output buffers. And when it's in read mode, you want to disable the input buffers and enable the output buffers. So how do you do that? So let's say, here I'll just draw a nice and pretty picture. So here we've got an individual cell right there with our select up top, and there's a bunch of cells to the left and right of it. I'm just going to do this for one of them. You got a data in and a data out, and where are they both going to? They're both going to this register through the data bus. Okay. So in, out register. And what the logic is for the input output here is this single thing off to the side, and we're going to say it's an active low write, active high read. Okay, so when we are going to do write, what is this guy? Well, it's a 0. And because that buffer has an active low indication on it, the input buffer is active, but this guy, like I said earlier, that acts like a drawbridge and it's open. So there's no possible connection between there and there. It's actually called a high impedance state, but just think of it like that for now. So basically now, when it's writing, you've got a path for this 1 or 0 or whatever it is to be stored in there when it's selected. Okay. Now on opposite, when it's in read mode, let's say we have a 1 stored in here. That write read line, input output control, goes to 1, and this buffer is disabled, and this guy is enabled, allowing that 1 to be stored in there. Okay, so there is a diagram in your book with a for a 3-dimensional asynchronous 32K by 8 SRAM, and then that has, let's draw that picture. It has 256 rows and 128 columns, and because it's 3-dimensional, it's got 8 floors. You know, just think about it's 8 floors to the skyscraper. So basically 32K by 8 SRAM, which is asynchronous for this particular application here. So again, that's 256 streets by 128 avenues, and you've got individual skyscrapers located at those addresses. So what is our capacity? Well, it's 256 times 128 possible intersections. So that's 32,768 different skyscrapers. And our true capacity really is 32,768 bytes. But we have taken the liberty of just giving ourselves a little bit of shorthand, calling it 32K. It's dropping all that. Basically, anytime that you've got a K in there or a mega, it's the nearest power of 2. Okay, it's a little bit of shorthand, a little computer shorthand. So now, what is the capacity of this particular SRAM? Well, it's 32,768 bytes, or 32K big B. Notice the capital B. That stands for byte. Okay? Did it again. But how many bit capacity is that? Well, that's 32,768 bytes times 8 bits per byte. Should give you 262,144 bits. Additionally, along with the 256 by 128 row 3-dimensional asynchronous SRAM here, there are some other individual commands here, particularly our chip select, which we did not discuss right here. All we discussed was our write and read. There's a write enable and an output enable. So that's equivalent to our read in our earlier. And that's our write. And this is kind of is the whole thing on, is the whole thing off. Okay. So whereas previously our simple analysis, we just had a single active low write, active high read. This one has 2 independent inputs, and our third one is the whole chip on, is the whole chip off. Okay, so immediately following this diagram here, we've got a couple of read and write cycle timing diagrams, and what this is illustrating is various necessary pauses for a system to basically properly execute a write or read. In particular, the timing, The more important ones is basically your TRC and your TWC. Basically, these are how long the address has to be available for the for it to read it. You know, oh, by the way, too, our previous example was two-dimensional, where it was 8 bits, which forms a byte in 8 rows. All you needed was a single row select. This guy is going to need a row select and a column select because it's three-dimensional. Okay, so to go back to what I was discussing here, our TRC and our TWC, read, cycle, time, write. Basically, those are the times it takes you. Where's that address? That address has got to be there for a certain amount of time for valid data to show up. You know, you don't want to be like, okay, here's this address, and then instantly take it away because you don't know if you've gotten there. You know, just think about a postman. He's got to look at the address on a letter long enough to figure out where it is. Okay, and that's kind of what the equivalent of these two guys are. So that was an asynchronous for the example there. And notice that there was no clock to it. There's something called synchronous SRAM. It's synchronized with the system clock, basically meaning the microprocessor is sending and receiving the same time the memory is writing and reading, and no one's waiting for anybody. It's a little bit more organized and efficient. There is 2 different types of synchronous, where there's a flow through. So in a flow through, so this is synchronous. Flow through, the inputs are synchronized. So in the case of a 8-bit input, the inputs are synchronized, and that's our output enable, write enable, our chip selects, etc., etc. Those are all synchronized with the clock, but our outputs aren't. So outputs are immediately available, regardless of, you know, and the advantage for that particular one is obviously if it just so happens to, you know, you synchronize these inputs, those inputs, and you get your output sooner than you would expect, sooner than the clock pulse, they're immediately available. That's in contrast to our pipeline. And that's basically the outputs are also synchronized. So even though it may have it, it's not going to be available until it's basically registered, clock registered into. So your outputs are also synchronized. Okay, so in, out, no, in, out, both in synchronous. Okay, so there's a couple other features, particularly our burst feature, which leads to a really good digression. So the M16A1 and the M16A2, those are rifles used by the military. What was the difference between these guys? Well, this one had a safe, a semi, and an automatic. This one had a safe, a semi, a 3-round burst. So basically, anybody got in panic mode with M16A1 went to full auto, fired their first shot, and the remaining 29 missed the target. Anyone in panic mode in M16A2 got to 3-round burst, and the first shot actually hit the target, then only 2 missed the target. Okay, so that's basically what a burst is basically it's taking a bunch of addresses and bam, hitting them. In this particular case, it's a 2-bit burst feature, which gives you 4 addresses, 0, 0, 0, 1, 10, 11. Basically, all it's doing is taking the last bits of the address. Let's say it's a, I don't know, like a, what is that? That's an 8-bit address. And it's keeping the first 6 the same, and it's just walking through this burst feature. So basically, this next couple skyscrapers, in the case of a 3-dimensional array, they're all housing the same data, where that's 0, 0, that's 0, 1, that's 1, 0, that's 1, 1. So basically, you're bursting all that data very similar to our, in this particular case, it's a 4-round burst rather than 3. You're taking 4, and hopefully they're going to hit the target. And it's going to store it into the 4 closest skyscrapers that happen to have 8 floors. There is the sequential addresses that are generated is simply a counter, 0, 0, 0, 1, 1, 0, 1, 1. I have no idea what the address burst logic is doing in your book. I don't understand that diagram, because that does not generate a 0, 0, 0, 1, 1, 0, 1, 1 sequence. Just use the counter. Basically, the last 2 bits for an address is just a counter. Okay, so a burst, all it is storing it closely related data into closely accessible closely accessible areas of the memory. So because SRAM is a little bit faster than our DRAM, and it's a little bit more expensive, so you want it on hand, but you don't want a lot of it, and it's often used in something called a cache. So a cache is something you use often, and that's why outlaw Josie Wales kept a 6-gun on his belt and not a frying pan, because he used the 6-gun a lot more often than he used the frying pan. That's what cache is. It's basically the most frequently used data or instructions. Or the most recently used data instructions, because chances are, if you're using it recently, you might need it again soon. And it's stored, all those recently used or frequently used, stored in very fast, very expensive SRAM called the cache. There's different levels. L1, muy caro, very expensive, but very fast. And that's kept real close, maybe even inside the microprocessor. So, expensive, fast, but not a lot of it, because it's expensive. But it's real close. Then there's an L2 cache, which is not as fast. As a result, it's not as expensive, but still pretty expensive. And just a little bit larger than our L1 cache. And that's not really as close, but still pretty close. So that's something that you're not using all the time, but you do want to keep it close at hand. Then there's other intermediaries, L3, L4, so on and so forth. But then finally you're going to get to main memory. And that's not SRAM. That's typically DRAM, which is slower but cheaper. And you've got more of it because it's cheaper. Okay? So as you progress down the levels, things are getting slower and cheaper, but you're getting more of it. because it's cheaper. You know, it'd be nice to have everything all in L1 cache, you know, because it's so fast, but you're not going to do that because it's expensive. Okay, so that's why you do this progressive structure there. L1, L2, L3, L4, so on and so forth, down to our main memory, DRAM. So now that we're talking about DRAM, might as well talk about DRAM. So DRAM, dynamic RAM. And as we discussed earlier, it's a little bit slower, but it's cheaper and smaller. Why is it smaller? Well, previously we were using a latch for its cell for our SRAM, which is in actuality a bunch of NANDs, NORs, whatever they are, which are a bunch of transistors hooked together. Well, DRAM uses a single transistor hooked up with a single capacitor, which is just two tiny parallel plates. Okay, substantially smaller because all it's using is two devices, a single transistor, in this particular case a MOSFET, and a capacitor. So if you've gone through ET 221, you should understand what a MOSFET is. It's actually one of my favorite devices. But if you haven't, all it is a switch. Just think of this as a switch. If there's a 1 on it, the gate, current can go that way or that way. If there's a 0 on it, it's turned off. There's no way current can get from one side to the next. Just think of it as a switch for now. Okay? So how is the dynamic RAM cell organized? Well, very similar to our SRAM, where this guy, that's our select, and that's our D in, D out. Okay? So if we want to write, put a 1 in there, we've got to select it, give it a 1. Let's say we're going to write a 1. So now this is a conductive path, and it charges up. Capacitor charges up to our 1. We want to go ahead and write a 0 in it, and there was a 1 in it before. Put a 0 there. We've selected it, and it discharges all the way down to 0. We want to go ahead and read it. Let's say there was a 1 on it. You got to go ahead and select it and figure out now our D out and D in, the same thing. Just basically, what is the signal here? Is it a 1 or a 0? Basically reading it. Same thing, if it was a 0, we want to read it. We've got to go ahead and select it and then read our 0 at our D out. Key thing for both of them, writing and reading, that selection. If it's not selected, there's no path between there. So you're not writing or reading anything. So if you try to put a 1 in there, not going to work. Okay? So the disadvantage of DRAM here, and the reason why it's slower, it requires a little bit more complex circuitry because a capacitor can leak. You know, basically a little leakage current there. And if you let it go long enough, all that charge is just going to bleed out of it. So that's why you need some refresh circuitry, which is like periodically topping off, like let's say that capacitor, the analogy I use, it's a leaky bucket. It's full of water, but it's kind of leaking out on the floor here. And it's equivalent to some little dude with a bucket coming by every 8 milliseconds. And if there's water in it, he's just going to refresh it by pouring a little bit more water in it. The only difference is it's not water he's pouring into it. He's got a little bucket of electrons, and it's not a little dude, so don't look for him inside there. It's the refresh circuitry that's doing that. So here's our buckets, here's our capacitors. One happens to have a 1 in it, one happens to have a 0 in it. And what you're going to do is basically, let's say it's going to bleed off in 10 milliseconds. So every 10 milliseconds that's going to go by, we need to select that particular row. And if it's got a 1 in it, or refresh here, it's going to have a 1. I can refresh that guy. And even though it's leaking out current right there, leaking out electrons, a couple more electrons are dumped in there until the next 10 milliseconds goes by. And while we're on this subject, I was going to talk about it later, but let's keep on talking about it, about the refresh. So every time you read it, you refresh it. So every time you read, you refresh it. Every time you write it, obviously you're refreshing it because you're putting the data in there. But in between these guys, you know, let's say it does take 10 milliseconds to go ahead and for it to disappear. If you don't read it or write into that thing, it's going to be gone. So what you need to do is every 10 milliseconds, whether it's reading or writing it, you need to go ahead and refresh it. There's 2 different ways of doing that. There's a burst refresh, which gets everybody. Every 10 milliseconds, the whole thing is refreshed. That's everybody. And every 10 milliseconds, though, those read and writes are disabled. You can't read and write while you're refreshing. And then there's this thing called distributed scheme, distributed refresh. And that's every row, at least once every 10 milliseconds, every row is getting refreshed, or every column, depends on how you want to do it. Let's just say, for example, every column is refreshed at least let's do row. Every row is refreshed at least every 10 milliseconds. So it doesn't mean every 10 milliseconds. It's talking about this guy gets refreshed while you can read and write to these guys. Then this guy gets refreshed. You can read and write that guy and these guys. Then that guy gets refreshed, but you can read and write that guy to those guys. So distributed takes a little bit more circuitry, but you're not temporarily paralyzed every 10 milliseconds. So there's, just like our SRAM discussion, there's a couple different types of DRAM. Obviously the first biggest distinction, asynchronous versus synchronous DRAM. Basically asynchronous, it's happening, and that's happening independent of the system clock. Synchronous, in sync with the system clock. Basically all the ins and all the outs are applied at every clock cycle. And synchronous DRAM is often, it's got a little abbreviation, SDRAM. So it's not static dynamic RAM, that wouldn't make sense. That's synchronous DRAM. Okay. There's also a burst feature, which I did not talk about EDO, so might as well talk about that. And I haven't even talked about FPM. So let's go take a step back here. So three-dimensional row, column. We can't just access it by row, so it's not just a row address. There's this thing called time division multiplexing addressing, where you get a single address bus coming in. But for the first half of its cycle, first half, it's saying the row. Second half, it's saying column. Okay, so that's all TDM addressing is. It requires two portions. There's two portions of the address. It requires a row and a column. This is for three-dimensional. Two-dimensional, you would just need a single one, a row, or a column. Depends on how it's organized. So TDM, two parts of an address. First half row, second half column. FPM is very similar to this. That's fast page mode. Very similar to TDM in that there's the row, but then column, 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 column. It keeps on going. So what you would expect for TDM is row 3, column 5. FPM, in contrast, is row 3, column 1, column 2, column 3, column 4, da 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 da, 1024. Basically, it's saying take all the columns in there, and it's saying right in here, right in that whole thing, that whole street. And that street happens to be called a page. You know, that's the whole page there. You're taking every column in that row. That's a page. Okay, that's basically making your addressing scheme a lot faster. You don't have to send a row, then a column. You can just send a single row and then a bunch of columns after it. That's very similar to what we learned here about burst. Basically, it's just saying 0, 0, 0, 1, 1, 0, 1, 1. It's taking the 4 proximate locations. So there's, well, I have to do EDO first. EDO is basically extended data out, very similar to fast page mode, but it allows the data from, let's say, this column to be used while you're looking up that one. Okay, so use this while you're looking up the next one. So it's just like FPM, except you can use data while you're looking up the next one. And then when you're looking up 3, you can use 2. When you're looking at 4, you can use 3. Burst is very similar to EDO, BEDO. Burst extended data out is taking 4 proximate rows. 1 or 0, 0, 0, 1, 1, 0, 1, 1, and all the columns in those rows. Just a faster means of writing and reading data. If you're already there, might as well write and read to that location. And because it's EDO, you can look up something or use that data while you're looking up the next one. Just something making it faster. Think that is it for RAM. There is just a quick one here. 1024 rows by 1024 columns. It's three-dimensional. So how many bytes can we put in it? So that's 1024 times 1024. It's 1,024,576. And because we're going to, and that's bytes, what is the abbreviation for that? It's 1 megabyte. I know that there's 24,576, but we're going to ignore it and just call it 1 mega, which is 10 to the 6th. But in computer speak, it's not really 10 to the 6th. It's 1,024,576. And that's 2 to the 10. That's 2 to the 10 if you remember right from your ET 111 powers of 10. 2 to the 10 times 2 to the 10. That's actually 2 to the 20th. Okay, so that's also this guy right there. Okay, let us move on to ROM.